Great.
Is everybody in? Everyone else outside. One step away from that. Hello, good afternoon. I'd like to welcome you to the last half-day session of the Faculty Research Week. So we've got several speakers today, this afternoon. I'm chairing some talks from Jerry, and Abir is doing some talks from computers, so we hope you find them interesting. And we have a keynote speaker, Luke Walsh, of Brainboxes. Now, before I talk a little bit about Brainboxes and get Luke to do the proper talking, Brainboxes deals with apps. What's that? They actually deal with something called like the industrial Internet of Things, more commonly known as Industry 4.0. And this is seen to be the future of manufacturing. Now, I'd like to take the opportunity for you postgrad students to recognise that as well as the teaching and the postgraduate training in things like manufacturing and computing, we do have outreach projects. In particular, we have a new project starting called LCR 4.0, which is going to help local companies try to take up some of the aspects of Industry 4.0 to improve their performance. And that's led by my colleagues Anthony and Leslie in the audience there. So this is not an academic project, but this is crucial to the university's vision of engaging with the community in the industry. And myself has also engaged partly with this project in something called Sensor City that some of you may or may not heard of. Sensor City is going to be a hub for sensor-based technologies and Internet of Things and big data. Now, what I'd like you to take away is that we are hoping that perhaps some of you in your research, whether it be in maths and apps, microwaves and sensors, even perhaps lasers and stuff, coming towards your end of PhD, you might think that you could somehow spin this stuff out. You might want to try to commercialise it. You might want some help. That's what we want to do at Sensor City. So please talk to your supervisors. Please take an interest in this stuff. It'll broaden your view of the world outside your own particular research, which is good, but it may provide you with a future career. But we are not necessarily the experts in this field, and we have with us Luke, who runs a company called Brainboxes, which have been for over 10 years helping companies connect their machines to the internet, amongst other things. Luke himself studied electronics with business management at York and became very excited about the future of technology. He then started looking at ways we can develop this, working with Hitachi, then working with Kaufman Global Scholars Program in the USA before founding Brainboxes in 2009. Luke is the managing director. It's based down near Speke, I believe, near the airport, and is working with many industrial clients to help improve their efficiency by the use of these modern digital techniques. So many people credit Industry 4.0 to Siemens in Germany. You never know, perhaps it should be credited to Brainboxes. So Luke,
thank you very
looking
much.
forward to hearing about it.
Thanks. Thanks for the introduction. Does that sound okay? Great. So, hi everyone, I'm Luke. I'm from a company called Brainboxes, and I'd like to talk to you today about Planet of the Apps, how the Internet of Things will affect your future. So I'll give you a quick overview. I'm going to quickly talk about who Brainboxes are, and then I'm going to paint you a picture of the utopian or dystopian IoT future. I'm going to tell you about what the Internet of Things is. I'm going to give you a brief history of data capture, the understanding or misunderstanding of data, hacking the Internet of Things, and finally your role as an engineer shaping the future. So first of all, Brainboxes. We're a British company. We're based in Liverpool in the UK. We founded in 1984. Pardon me. We've got an office in the USA and Japan. We're a family business. 40% of our staff are in R&D. We on average produce 1 new product per month. We're heavily focused on lean manufacturing. We have our own production line in Speak. On this line we can make 800 products a day. And we have in-house hardware design team, software design team, and we can customize. What we like to say to our customers is we can customize our products to fit their specific needs. So that's a little about us. We've got accreditations and we work with some big companies you might have heard of. But here's 2 applications which are science and engineering based, where our products are used. Our products are used in the Large Hadron Collider. Ethernet to serial products are used to control the mirrors as they bend and focus the beam as it goes around the track. And one of our guys in our company told me that they're also used to communicate with the supermagnets. So that's really interesting. The other area with a scientific engineering background, our products are used in the Atacama Desert by the Max Planck Institute. The Atacama Desert is the driest place on Earth, and you want to spend as little time out there as you can. So our Ethernet to serial products are used to monitor and control the huge telescopes that are on the Atacama Desert. So now I'm going to paint you a picture of a day in the life of you in 5 years from now when you're immersed by the Internet of Things. So you wake up at 8:29 by your sleep monitoring Garmin smartwatch, which detects your circadian sleep cycle and wakes you knowing the time you wish to rise, your current night's sleep and your optimal sleep requirements. You then walk into the bathroom. You're not in a daze because you've been woken up at a perfect time, and you stand on your weighing scales. Clearly this is not my weight, it's reading out. It shares your data with Tesco, and Tesco decides to order the low sugar biscuits next time. You pick up your internet-enabled smart toothbrush and brush your teeth, and the app on your phone gives you a reward, vouchers for the dentist. And this is because you have brushed your teeth 3 times a day, every day for the last month. You jump into your Tesla autonomous electric car. It drives you to work, and on the way to work detects there's a traffic jam up ahead and you're going to be delayed by 20 minutes. So it automatically sends a message to your Microsoft Office assistant, who cancels your morning meeting and reschedules it for later in the day. When you get to work, one of the machines on your production line advises you that a motor is about to fail. But don't worry, it's automatically ordered the replacement from RS, and it's on the way in the post. It'll be with you tomorrow. Then your Garmin smartwatch buzzes and reminds you that you've made a commitment to walk half an hour every day. And if you do this, the data is automatically linked to your insurance company, and you'll get lower insurance premiums on your health. Back at work, you review your smart monitoring of your production line, and it informs you that when Bob is running the night shift, you have more productive periods than when Jim is in charge. Maybe it's time to fire Jim. The government has a feed on your data and therefore already knows you're considering this, and the government has preemptively mailed Jim with job training advice. You jump back in your car, it's autonomous, it drives you home, and it communicates with your smart Nest thermostat and tells it that you're on the way and to put the heating on in your house. You step out of your car, the car automatically opens your garage door, it drives into your garage for you, your garage door closes, and the car automatically connects to the charging point in the house. Now the charging point communicates with the national grid, and it will only charge your car at the time of day which is cheapest. As you step into your house, now the crazy thing is this really exists, you use your Febreze Internet of Things enabled smart app, and you turn up the sweet smelling level of the Febreze in your house. Later on that day, you notice there's some mail at the front door. The NHS has mailed you a personalized test kit, as your Internet of Things fridge has informed them that your recent diet change has likely meant that you have a higher likelihood of liver damage. So is this the Internet of Things future? Is this what the companies you're currently seeing in the media and in this industrial and consumer-based space, is this their idea of what it is and what will be sold? Well, the Internet of Things means a lot of different things to a lot of different people. There is no one definition of what it is. So instead, I'm going to give you my definition. For me, it's the best one. So what is the Internet of Things? It's any device that can connect out to the internet and can monitor and or control something. So in the consumer world, those some things you may already be familiar with. The Google Nest thermostat. It uses Wi-Fi to communicate with the cloud and let you know the temperature in your home. Your Skybox can be plugged into the internet and then you can automatically record programs through an app on your phone. GE provides smart lights that can be turned on and off. And Withings provides the weighing scales that send your BMI and your current weight to the cloud. So according to Gartner, who are a research institute, by 2020, there will be 20 billion devices connected to the internet. Now today, there are currently 5 billion devices. So where are the other 15 billion going to come from? That's the big question. Or think back 5 years. 5 years ago, you probably didn't have internet-enabled television. You probably didn't watch YouTube on your TV or Netflix or BBC iPlayer streaming over the internet. Today, it's absolutely commonplace. And in 5 years from now, well, 4 years from now, there'll be 15 billion additional devices connected to the internet. So this is on the way, according to Gartner. And they call this kind of trend the Gartner hype cycle. So this is any new technology that's introduced to a market that promises massive disruption in the industry. So this current hype cycle we're going through is for the Internet of Things. Now initially there's a technological trigger for the hypercycle. In this case it was the combination of cheap electronics and easily accessible connection to the internet. This led to a peak of inflated expectations where all of a sudden this newly coined word was going to solve all of your daily problems. Shortly thereafter, the industry falls into a trough of disillusionment where you realize it's not going to solve all of those daily problems. In fact, it's not even going to solve half of what I've probably described to you in the previous slides. And then finally, over time, the market finds a useful, meaningful, productive use of the technology. So where are we today with the Internet of Things? I would say we're firmly here at the top of the peak of inflated expectations. If you go to any industry shows, every stand you go to, there'll be someone on the stand saying, yes, we have an Internet of Things device, and yes, we're going to use it to solve all of your problems. But this hypercycle is not new. 10 years ago, Bluetooth was a part of this hypercycle. I went to a talk back then where Bluetooth was going to be used to pay your bills and for you to find people in your vicinity or be advertised to. And of course, Bluetooth never did all of those things, but it is still everywhere today. Bluetooth has found a really good use case, and that use case is connecting your phone to your car, or your phone to a radio system, or your phone to a headset. So those are the predominant uses of Bluetooth. It's gone through the hypercycle and it's found its plateau of productivity. Another hypercycle we're in right now, this one has happened before, is for virtual reality. 15 years ago, people were telling you virtual reality was going to change your world. It never happened. And now, here we are again. On the right, we've got a HTC Vive, and on the left, we've got an Oculus Rift. Both these devices offer an immersive 3D environment in which you can play your computer games, or you can model a car cockpit, or you can produce a virtual factory and see how products will flow down your production line. Will this be the real coming of the VR age? Well, I don't know. But people definitely think it's going to be the coming of the internet age. Now, according to the analysts, a bigger sector than the consumer Internet of Things will be the industrial Internet of Things. So here's the division. This is what National Instruments thinks the division is. On the right-hand side, we've got what they think is a part of the consumer internet. These are most of the use cases I explained before: phones, wearable technology, home appliances, TV, fitness devices. And on the left-hand side, we've got the industrial Internet of Things, which encompasses the smart grid, factory automation, Industry 4.0, smart cities, and smart medicine. But a really good example of this use case that's in action today is Siemens' partnership with Pilkington Glass in St. Helens. Pilkington is a huge factory in St. Helens. They produce glass. They're one of the biggest producers in the UK, if not the biggest. And their biggest expense, their biggest raw material cost is energy. And so Siemens partnered with them and said, if we can reduce your energy bill by 10%, what's that worth to you? And it's worth a huge amount of money. But Pilkington don't want to invest the capital in doing that. So instead, Siemens said, okay, we will monitor all your energy systems in your factory. We will send that data back to the cloud, and from Germany, we will analyze your energy usage. And then based on that, they would suggest projects for Pilkington to undertake to save money. But not only would they suggest them, they would pay for them. And Pilkington only have to pay them back once they've made a saving, and they only have to pay them back out of the savings they make. So this is a good deal for Pilkington. It's also an extremely good deal for Siemens because they are starting to understand energy usage in factories, and they can apply that knowledge that they've learned elsewhere too. So what does the industrial Internet of Things mean to Brainboxes? Well, here's a brief example. There's a machine on a factory floor, like so. One of our devices connects to the machine and monitors and controls the signals on that machine. The device then securely connects to the internet, and then from the internet, any user who's authenticated can securely connect to that same cloud and review and analyze their data. So that's a very simplistic overview of how we view the Internet of Things. And here's an example of where it's in use today. There are many factories that have CNC machines. One of our modules is connected to that CNC machine. The CNC machine is producing data about how productive it has been, and our modules analyze those signals. And likewise, factory floor workers need to send programs to the CNC machine, and that all comes over the network and into the machine through our module. Again, here's another use case where our products are used. In America, approximately 50 hospitals in their clinical kidney dialysis suites. Each machine is connected to one of our devices. Our device then connects to a PC. Now, the PC is constantly monitoring the signals from the kidney dialysis machines, making a secure connection to the cloud and sending the data up to the cloud. This offers huge benefits in medicine, particularly to the nurses. Previously, they were going around with clipboards and then with iPads, and they were reading the information on each one of these screens, and they were typing it into their iPad. Now, of course, a nurse has a lot better things they need to be doing, and sometimes they're pulled away on an emergency elsewhere, so they're going to miss some of the data. With this approach, all the data is captured, and if there is any issues that need to be observed, the data can be sent to another clinician in a completely different part of the country who can analyze the data and make a suitable prognosis. And again, this is another application we're involved with. One of our partners called Mechline has this machine called the Waste 2.0. What this machine does is it saves you having to throw food waste in the bin. Food waste is a very expensive thing to dispose of, and it fills landfill, and it costs companies money, and it's bad for the environment. So Mechline have provided this machine which mechanically churns the food, and in addition it has various enzymes in there that digest the food and turn it from food waste into wastewater that you can flush down the drain. And so rather than paying to take these bags of food waste away, you can flush them down the drain very cheaply. And our device monitors this machine, and using a Raspberry Pi as a gateway, sends the data to the internet, and then on the internet the user can easily see how much money they've saved, how much food waste they've prevented being thrown into landfill. So, I mean, in summary of that section, the application, the app, is the interface between you and the Internet of Things. So currently apps are on your phone. In an ideal world, the app would disappear. You wouldn't even be really aware it was there. It would be a thin interface between you and your data. So on that note, I'm going to give you what is my view of a brief history of data capture. So, or put it another way, the problems don't change, only the technology to solve them. So in the example I've given, this is this part of the setup. Your machine has lots of signals in it. You want to get those signals and make sense of them. How do you get the information out of the machine and put it somewhere? So where does this come from? Well, one day the boss comes to his production manager and he says, we're not making enough products. The production manager says, yes, we are. We're working really hard. The boss says, prove it or you're fired. So the production manager goes away and thinks, right, I need to start measuring how well we're really doing. So in the early days, 1900s onwards, this was the most sophisticated data capture available, a clipboard and a pen. Someone would stand at the end of a production line, and every time a product went past, they would tally on a chart to say, yep, that's one. And at the end of the day, they'd total it up and they'd give it to their manager, and their manager could definitively say to his boss, today we have made 20 products. Technology's moved on since then. We now have data capture computerized. This is in the 1970s onwards. But like Homer Simpson here, there's still often a human required to input the data into the machine. So in this example, Homer Simpson is sitting in the nuclear factory. Every time an event occurs, he has to press a button, and then the computer logs the data. Now, in these two previous instances, you'll find that for an employee doing the job, it's extremely monotonous and boring. There's a likelihood that they'll fake the data, and there's also a likelihood they'll get very bored and stick pens in their ears. Now, moving on to the 1980s onwards, data capture became a little more automated again. Rather than a human having to capture the data, instead a sensor can start capturing the data. So in this case, the sensor is detecting when a box passes by it on a production line. The sensor is connected to some large display hanging from the ceiling in the factory, and the display displays the current number of things produced that day. Unfortunately, this information is not stored anywhere, so still at the end of the day, the production manager must come by and write that number down on a piece of paper. But we're making progress. In the 1990s, the advent of the coming of age of the Windows PC, we realized we could connect the sensor to a PC in the office. And now we can record all this data generated by the sensor on the PC in the office. And whenever the production manager likes, he can walk up to that one PC that has the information, look on the screen and look at the wonderful Excel graphs and charts generated by all that data. Still suboptimal. So in 2000s onwards, we realized we could connect that PC to the internet, which wasn't called the cloud then, it was just called the internet. And then from the internet, we can view the data on a mobile phone or a browser or any kind of device screen. Now, so what's the difference between this and the Internet of Things? Well, the difference is you'll notice the PC is gone. And rather than there being another step in the process, you can now get the data straight from this sensor and electronic component straight to the cloud. So this is a much more optimal solution. It's much cheaper, and it means you can put your sensors in more places. So in summary, the problem hasn't changed. In this particular instance, the production manager wanted to count products. It's just the solution and the technology used to do it that's changed, and the cost and the availability has changed dramatically. But now we're capturing data, and the boss says to us, now I can prove we're still not making enough products. So now it brings us on to the next section, which is understanding and analyzing the data in a correct way. So you're now capturing tons of signals. What does it all mean? And this is another huge engineering challenge. So this is Brainboxes' view of data capture first. So we see it as there's 4 layers of machine data generation and capture. Each layer is built upon the layer below. So the lowest layer of data capture is the second-by-second machine signals. So maybe the fan's come on, maybe the green light's gone off, maybe the motor has started to vibrate a little bit more than normal, maybe the proximity sensor's detected an object, maybe the temperature's gone up by a degree. If you were just to look at one snapshot of this data, the signals are moving so fast and rapidly, it almost looks like noise. So we need another layer on top of it to interpret it. So the next layer up is machine state. So if I interpret the individual signals, I can make come to a conclusion about what my machine is currently doing. So for example, if the fan's on and the green light's on, well, that means the machine is running. If the machine is running and the sensor detects an object, that means we've just produced the product. So at this level, the signals are changing slower than at the level before, but they're still changing very rapidly. And unless you've constantly got your eyes on the screen, you're not going to see everything that's happening. So you need a layer above this, and that layer is statistical layer. So that's analyzing the machine's state over time to come to conclusions about what's happening. So for example, you may say, well, the machine's been running 45% of the shift. Or you may say, judging by the number of products we've made this shift, we on average make one product every 89 seconds. Or you may say, the machine started 30 minutes after the shift start. Or you may say the overall equipment effectiveness is 35%. So again, this is really useful data if you're on the shop floor as the production line manager. And it's really useful if you think you've got a problem today. But actually, there's another layer above that which is more important, because over time, you'll find the data is very similar day to day, and it won't be interesting anymore. So you need a layer above that, and that layer is insights. It's analyzing these trends over time and understanding what's changing and informing somebody about the change so that they can understand why it's happened. So, for example, Tuesday night shift is less productive than the day shift. This is similar to before when I said we had to fire Jim because he's less productive. Well, if you were to look at the data more closely, you might discover that after the day shift, the fan and the oven are extremely hot, and because of that, they produce less. So maybe the actual answer to this is you need to reallocate the resources so that that doesn't happen, or you need to plan maintenance of the machine so that it doesn't get into this overheated state. The other thing that the data might tell you one day is there's an unusual level of breakdowns at one particular summer on one particular machine, and then you can go into the detail and figure out why. So that's from our point of view are the 4 levels of data capture. Brainboxes as a company, we're a hardware company. We see software as a key to selling the hardware. Ultimately, these apps that we generate to sell the software should disappear into the background. You shouldn't really notice them. If everything's working correctly, don't look. If you don't want to know the time, you don't have the watch in front of your face all the time. So it should all disappear into the background, and only when something unusual and noteworthy and important happens should you need to know about it. Which brings us on to misunderstanding the data. So on the analysis layer and the insight layer, there's all kinds of ways you can misunderstand and misinterpret what's going on, which is another key area where engineers are really important to understand the nature of all this data being generated. So I'm going to summarize this with 3 case studies. The first one is 1% false positive. The second one is missing bullet holes, and the third one is the Monty Hall problem. So 1% false positive. I've got a question for you in the audience. If I have a clinical test that can identify a disease with 99% accuracy, what is the chance of a patient diagnosed with the disease actually having it? So if I run my test on a random member of the audience and it says they have it, what's the real chance that they actually have it? Is it 1%? Because it's 99% accurate, it must be right. Is it 10%? Is it 20%? Well, the actual answer is that I haven't given you all the information.
We don't know about this one because there's no specificity.
Yes. You need to understand your sample and your population. So one excellent way to explain the problem is take a population of 10,000 people where 1% of those people actually have the disease you're looking for. So in this population of 10,000, 9,900 have no disease. 100 actually have the disease you're trying to detect. So now if I perform the test for the disease on all these people, let's see what the results of that test look like. Well, of the people who don't have the disease, the test is 99% accurate. So it will correctly say 9,801 of them don't have the disease. but it will incorrectly say 1% of them do have the disease. So it will incorrectly say 99 people out of this undiseased section of the population have it. If I then look at the 100 who do really have it, and I test all them, it will incorrectly classify one of them as having no disease, but it will correctly classify 99 out of that 100 as having a disease. So according to the test, which is 99% accurate, in a population of 10,000 people, where 100 people really have the disease, according to the test, 198 people really have the disease. So again, I'll ask the question, if I have a clinical test that can identify a disease with 99% accuracy, what is the chance of a patient diagnosed with the disease actually having it? Well, the chance is 99 out of 198. So if I pick a random person who is being diagnosed as having it, there's only a 50% chance they're really ill. Now that matters a huge amount, particularly if the disease is something really serious like HIV. So the key point here is that as an engineer and a scientist, you have to be really careful to understand what your data is telling you. And you have to be really, really careful when explaining it to the public. Because if I were to say, a test which is 99% accurate has identified me as having a disease, personally, I'd feel like I must have it. Okay, the second story is called The Missing Bullet Holes, and I'm going to paraphrase this story, butcher it a little bit. During World War II, the American Air Force was sending bombers over Europe to drop bombs on Germany. However, they wanted to reduce the number of deaths and the number of lost planes that crashed as they were bombing the enemy. So what they did was they used a mathematician to analyze all the bullet holes that appeared on all the bombers that landed back at the airbase. And his job was to figure out, where do I put extra armor on this plane to make sure that we save more planes and more people's lives and more of them come home. Now, looking at this data, here is where all the bullet holes occurred. But there's a key to this data, and the key is, these are the planes that came back. So you need to put the armor where you don't see bullets, because when they got hit in these locations by the bullets, they survived and they came home. When they got hit, for example, in these locations around the engines, they didn't survive, they didn't come home, there are no bullet holes in the sample. So the key to this data is to put the armor where there is no bullets. So you need to understand what your data is telling you. Now, the third problem I'm not going to tell you the answer to. I'm going to leave you to see if you can figure it out. You can always Google it. This third problem is called the Monty Hall problem. And it's named after this game show host, Monty Hall. And it's a paraphrase of his game show. So the winning contestant of the night on the game show gets to the final round. And in the final round, Monty Hall says, I have 3 doors, A, B, and C. Behind one of those doors is a super sports car. Behind 2 of those doors are llamas. All you've got to do is pick the right door, A, B, or C. So maybe you take a guess. Maybe you choose door B. Now, Monty Hall, the guy who's running the game, he knows everything. And what he will now do for you is open one of the other 2 doors to reveal a llama. And Monty says to you, would you like to stick or twist? And it's up to you whether you should stick or twist. One is statistically much more likely to yield a good result than the other. Now, this particular problem baffled mathematicians for years, and there's a really easy to explain solution to it. And if you're interested, come and ask me afterwards. Llama or car? Okay, finally, we've talked about the data capture. We've talked about understanding the data and analyzing it and presenting it to the user. One of the key things with Internet of Things devices is data communication. All this data is flowing over a public network. Anyone on that public network could review the communications going over it, could tap the wires. We've all heard stories in recent years about Edward Snowden and the NSA and GCHQ. So how do you ensure the data is safe And what anecdotes might we have of people who have got it wrong? Well, this section is called Hacking the Internet of Things, or Security is really difficult and often overlooked. The takeaway from this section, I hope, will be never try to do security yourself. It's really, really challenging. The 5 topics I'm going to cover are cars, windows, keys, cameras, and TVs. So first of all, cars. So earlier this year, Wired released a report which showed that a hacker from a laptop could take over any Chrysler Jeep in all of America and press the brakes. So how is that even possible? So in this particular example, we've got a reporter driving a car. The hacker then takes over the car and slams on the brakes. And he's just using a laptop. The reason for this is that all cars are a part of the Internet of Things. They all contain SIM cards, modern cars. They're all getting over-the-air updates with the latest software. And there was a flaw within Chrysler's entertainment system which allowed the hacker to gain access to the car. Once they'd gained access to the entertainment system, they could then gain access to the car engine systems. No cars are driven mechanically anymore. When you press the brake, you're not really pressing something that controls a brake. You're telling the computer to press the brake. And so you, as a hacker, you can tell the computer to press the brake too. And so that's how this particular incident happened. Chrysler had to recall, I think, 100,000 cars. They also offered, they couldn't fix the problem themselves over the air, even though that's how the problem occurred. So they sent USB keys to all Jeep owners' homes, hoping they might do it themselves. Great. Okay, who's got Windows 10? Show of hands, great. Okay, so Microsoft in their Windows 10 operating system has this setting on by default. Don't know if you've seen it, it's called Wi-Fi Sense. And what that means is, if you've typed a password for a Wi-Fi network into your Windows laptop, by default, it will share that password with any of your contacts on Outlook, with any of your contacts on Skype, or with any of your Facebook friends. Do you want some of those random Facebook friends you met years ago to walk into your house with their laptop and magically connect to your Wi-Fi? I don't think so. So what I advise you do after this is go back to your office and check that setting and make sure you untick these 3 boxes. For networks I select, share them with my. And by the way, networks I select is all of them by default. Keys. So there's 2 well-known hacks of car keys in the last few years. One of them is called a replay attack. The other one is called a signal amplification attack. A replay attack is for older models of car, where the wireless car key and the car are both pre-programmed with the same random seed. So this is a random initial start value for generating codes. So when I press my car key, it produces a random value, which the car will recognize because it has the same random start value. So press the key, the car opens, and it means that if I press another key, the car won't open because the random value is completely different. However, if I were to press this key now while it's in my pocket, my car hasn't seen that code yet. So it's still waiting for it and expecting it. So someone can come up to your car keys while you're away from your car. They can press the open button, record the code. They can then walk out into the car park and replay the code, and whichever car opens, thank you very much. The second way of doing it is with more modern cars. Some really modern posh cars, the key, you just have to be in the vicinity of the vehicle and it automatically opens. So the security protocol to enable this opening is very sophisticated. It uses all the latest modern technology, but there's a subtle flaw. It's all about proximity. So what hackers did was they made a suitcase that could amplify signals. They stood outside very posh homes. They pointed the suitcase at the home to amplify the signal that's always coming from the key, and then they amplified it and sent it to the car. The car said, oh, the key's near me, I should open. So the car opened, and then the hacker stepped into the car, and the car said, oh, the door's open and the key's near me, I should turn the engine on. So it turned the engine on, and then this hacker drove away in the car. And there's a number of videos showing really posh cars seemingly magically opening outside of people's houses, and it's because of this type of attack. Samsung smart TVs. Who has a Samsung smart TV? Anyone? Great, you need to check this setting when you get home. Samsung smart TVs come with a voice activation option. So if you connect your TV into the network, you can talk to it and tell it what channel to go to. However, in February of this year, Samsung issued a warning to its customers to avoid discussing personal information in front of their new smart TV. So you're in the comfort of your own home. Samsung's solution is not, I'm sorry, we're going to disable this. Samsung's solution is, please don't have private conversations. And not only that, in the terms and conditions for a Samsung TV, it says they may share your data with third parties. So beware. Bonus, smart toilets. So as you know, the Japanese are very keen on smart toilets, and this is a Japanese smart toilet called Satis. It allows you through an app to remotely operate the toilet, open the lid, close the lid, flush the toilet. So it's very hygienic, you don't need to touch it. But there's a subtle flaw. Satis left the default Bluetooth password as 0000. So anyone can connect to this toilet and flush it. Yeah. And this is a little bit more terrifying. If you have an internet-enabled webcam, I would strongly advise you to do a quick Google search to make sure it's not compromised, because lots of internet-enabled webcams have very poor security. And in this story, the parents were using this FOSS-cam to monitor their child while they were sleeping, while the parents were downstairs. Someone had hacked into the camera and was talking to the child. And it was only when the parents walked up to the bedroom, they heard someone say, "Oh, someone's coming," that they realized they had a problem. And FOSS-cam admitted they'd made a mistake and they had insecure security on their camera. So yeah, my advice on that is, don't connect a camera to the internet. It's not worth it. So in summary, you need to be careful what you IoT enable. Does it have to be on the internet? Do you need a smart toothbrush? Security is really, really difficult to get right. Companies from large to small all get it wrong. If somebody asks you to make a security protocol, the first response should always be no. And something is only as strong as the weakest link. So we think about what other third-party hardware and software you're using in your system, and does that have a weakness? You might have made your part of the system super secure, but somebody else may have introduced a flaw. So finally, your role as an engineer shaping the future. This is one of my favorite Dilbert strips. The manager says to Dilbert, "I hired an overqualified yet incompetent guy to help on your project. I was happily incompetent for years, then I got my PhD, and people started to think I could do things." And okay, I'm stumped. So this is a challenge for you guys, is that for the Internet of Things, engineers are needed in all aspects of this technology. Hardware engineers to create the electronic components, material engineers to create the sensors, software engineers to create the cloud protocols, and data engineers to analyze the data, communication engineers. Engineers are required everywhere in this process. But a small warning from the music industry before we finish. 100 years ago, you only had to be a good singer in your local village to get paid. What do I mean by that? 100 years ago, people have always enjoyed listening to music. They've always enjoyed listening to good music. And people have always been willing to pay for the privilege of doing that. 100 years ago, there was no internet. There was no CD technology. There were, maybe go back a little bit before radio, there was no broadcast. And so people would go to their local bar to listen to their local singer, and they'd pay him for the privilege of doing that. Today, that model has completely changed. Today, you have to be in the top 1,000 singers in the world, and you are paid extremely well. However, everyone else gets nothing. And this comes straight from the Spotify's own website. It says the chart below shows the decline in the recorded music industry scene since 1997. Whilst the growth of digital downloads has replaced some of this value, the majority of revenue in the industry has evaporated. This is This rapid decline is not due to a fall in music consumption, but a shift in music listening behaviour towards formats that do not generate significant income for artists. So why is this a warning for engineers? Will the same happen to data scientists, for example? Today, in a particular organisation, as a data scientist, you get paid extremely well to analyse the company's data and provide advice on decisions the company should make to improve processes or save money. In the future, all that data may go straight out of your company and straight into Google's cloud platform or IBM's Watson platform or Siemens cloud platform and analysed by their top 1,000 engineers, who will all be paid extremely well. However, everyone else gets nothing. So it's a warning from maybe 10 years from now, and it's something to bear in mind. But engineering has never been more important. If there's going to be 20 billion devices by 2020 connected to the internet, we're going to need all these different types of engineering capability, and that is represented in this room. So my end point today is engineers are the third best paid profession to be in, after doctors and lawyers, I believe. So it's a fantastic job decision to make and career opportunity, and I wish you all the best in your futures. Thank you.
Okay, so we've got 10 minutes or so. I hope that Luke's very interesting talk may have inspired a few questions. So, anybody got any questions for Luke? Yes? Yep.
Yeah.
I've seen this empirically before in Gartner. How confident are you
All right. Are we really at the top? Is that what you're asking? Are we? Well, obviously my data is anecdotal, and many anecdotes does not equal data. But from what I have seen, whenever I go to industry shows, everyone is talking about the Internet of Things, and everyone is saying how their take on the technology is going to solve the problem. So I do believe we're at the top of the hypercycle. 15 years ago, Brainboxes was also in the Bluetooth industry, and we were the first company in the world to have 6 fully qualified Bluetooth devices. And many people thought that Bluetooth was going to be the thing that solved all the world's problems, but it didn't. I'd be very upset if we're here, for example, because there's going to be a lot more hype until it finally reaches the right place. I firmly believe we're around here.
So would you put 10,000 worth of cut options on this thing at the moment?
I'm putting it all into the company. So in a sense, yes. But yeah, if I had more wealth to allocate, then yeah, maybe. Yeah. Yes.
In terms of the Internet of Things and these 20 billion devices, how many do you think what percentage relies on satellite communication?
It's difficult to say. A lot of internet connections ultimately go through a satellite, or a lot of telephone GSM connections may end up at a satellite. So quite a fair percentage. From an industrial user's point of view or a customer's point of view, you're connecting often to your local provider, but who they end up going through is entirely up to them. So probably a significant amount.
So to lose satellite communication would be a catastrophe?
Yeah, quite possibly, yes. I imagine so. Yeah, I mean, there are undersea cables connecting most countries, and a lot of data flows through them, but probably a significant quantity also goes through satellites.
Any more questions? Yes?
What major steps do you think should be taken regarding the actual security of the kinds of devices you've described? Because, as you said, even with computer-controlled cars that weren't constantly connected to the internet, hackers were still able to access them. So in cases where everything we do is connected and there's 20 billion devices, how do you think the problem is going to get worse? And what do you think needs to be done? I mean, our current strategy is really...
Yeah. There's on one hand, there's a trade-off between convenience and capability of a product. So you're giving away some of your privacy to other people when you sign up to use their product. And on the other hand, you're relying on them to ensure that they don't spill any of those details out. And there are a number of key things required to make a secure system. But thinking you have them and still finding an exploit in the system are two different things. So for example, all communication must be over an encrypted channel. But what level of encryption do you choose? I might choose something today that next month they discover is compromised. And so whatever technology you choose, it must be field updatable. But if something is in the field updatable, that clearly shows there's a route into the product from the outside. So that could potentially offer a compromise point as well. Not only should it be cryptographically secure, there must be a way for each thing to uniquely identify itself, and for the server to uniquely know that it is definitely talking to the thermostat in my house and not in a different house. And there must be a clear way that I can show ownership of a thing. So through the internet, I need to clearly provide the cloud with a method that which I can clearly demonstrate I own that thing. So there are a number of parts to the system, and each one has to be done properly. And probably, because there are so many pieces in the puzzle, probably they'll never all be done properly.
Do you see that as a big future for your company, supporting that kind of security, especially for the industrial? Although we talked today about the Webcam and the cars, but there's also been instances where, like, related security attachments, where industrial pieces of equipment have been attacked. I mean, is that obviously a concern? Do you see that as a potential base for companies?
Yeah, I mean, currently we focus on hardware and we use software as a means to sell it. And we want to make sure that any supporting software is up to the task. But there is a huge industry out there for security, absolutely massive industry. And it could be something we look at, but we might leave that to other companies. It's unclear at this point.
Just in terms of what you provide at the moment and how that might develop in a positive or negative, you gave the example of making gun equipment smart, so the machine tools or the dialysis machines, etc.
Yeah.
Is it likely that you and the equivalents, obviously Siemens with a bigger scale version,
Oh, yeah.
are you likely to stay at that sort of functionality, or will your devices be built into the machines that are sold?
Yeah, I mean, ultimately, technology gets smaller and often gets combined. You just have to look at the number of devices functions that your smartphone performs today that you had to have separate devices for 10 years ago. So ultimately, there must be a pathway where this technology becomes embedded in the thing. But there are so many pieces of industrial equipment out there that people bought in the last 15 years that costed them £1 million. Why would they want to upgrade it just for a network connection when instead they can, for a small outlay, add that functionality onto the machine? So I see that part of the market being there for many years to come, just because of the price of the asset that you want to monitor. And there's no reason a company should give up something so expensive just for a little bit of extra functionality.
For the Internet of Things, very good is for monitor something happen there. Now, if some process need a quick decision making, and how quick current level response can be.
Yeah, well, on the internet, latency is a very big deal. And so if you want real-time control of something, you're much better off using something more traditional like a PLC. For fast response times, you're much better leaving the intelligence as close to the actuator as possible. Over the internet, over a corporate network, you might get a 2 millisecond response time or a 6 millisecond response time. And for some machines that are doing some high precision things, that's too slow. Over the internet, you can't even guarantee that. You might get a second in real bad situations, or if you've got a GSM signal, really slow. So IoT is great for monitoring, and it's good for control in some situations, but there's lots of situations where it makes no sense, I think.
One more question? Okay, does Internet of Things change the business model, of companies? Because I was talking to somebody yesterday who said, like for Siemens, it's moving away from the drives as such. It's about them gaining a monopoly on your data and your monitoring of data, analysis of data. Do you see a similar sort of vision?
Yeah, absolutely. I think Siemens' biggest worry is probably that someone like Google will buy them, because traditionally Siemens are a hardware company. They make motors and controls and actuators and all kinds of physical goods. But the value in the future doesn't necessarily come from the hardware. It comes from the understanding of the data. So I absolutely agree with that. And they're right to be worried, and they're right to look at new business models. And this one they're doing with Pilkington makes a huge amount of sense. So, I mean, Siemens are a huge company, but compared to some of these American software companies, they could be bought. So they should be worried, absolutely.
Okay, we're going to leave it there. I'd like to thank Luke for a very interesting talk and a good discussion afterwards. And obviously, I hope Luke's around for a little bit longer.
Yeah, I have to go in an hour, but I will be around.
So try and catch him if you've got any more questions. Thank you very much, Luke.
Great, thank you.
Yeah, I sort of thinking of staying through to and talk to an empty room at this rate.
We'll chase them back in. This is
Yeah, I'm likely to stay. I mean, I've got a customer down in the lab which I hope to go and check out on, but if I check out on, I'd quite like to sit here and see some prizes given out. So let's just carry on. So I'll get the first one on. You then introduce Christopher, and we'll sit between them. Yeah. Okay. I think it's okay. Do you know who Philip is? I don't.
Do we,
Wonder if that
let me
does-
see. Do we have Philip here?
Yeah, please. It's a pointer.
All right. Let's see.
Is your presentation on?
No, it's not. But yeah, it should be on here. Fn plus F5.
What's it called?
It has a grotesquely long title. Faculty. What's that? Faculty research.
Oh, PM.
Philip Taylor.
Okay, so 6 to 10 minutes, keep an eye on it. So if you're running out, I'm going to sort of give you some visual clues so if I'm saying things. Quickly speed up and cut short if need be.
Okay.
Okay, so we're coming to a presentation on first presentation free from Jerry. So Philip is going to talk to us about a review of the capabilities and limitations of general experimental techniques for measuring turbulent flow over textured surfaces. Thank you for that. How do we see it on the screen? Have you got an F5 for it?
Yeah, so. Right.
No, we've got to start now. We've got to keep the time. There you're on.
Hello, my name's Philip. I'm currently working in the field of fluid mechanics and aerodynamics, more specifically looking at the use of textured surfaces for drag reduction in cases such as aeroplanes, ships and cars and even bearings. So a brief overview of the presentation. I'm going to start by introducing some common surfaces that have been shown to reduce drag over a smooth surface. And these are surfaces which have been inspired by the drag reducing properties of shark skin. And then I'm going to talk about some common experimental techniques we use to analyze the skin friction over these surfaces. And then I'm going to talk about the additional complications, errors and limitations which occur when we move from smooth surfaces to textured geometries. So I just want to give you a brief overview of what we mean by drag. Of what we mean by drag from fluid flow. As fluid flows over a solid surface, the fluid right next to the surface becomes stationary. Let's make it worse. And this creates a velocity gradient between the solid surface and the velocity of the outer region of the which we call the free stream.
By matching up experimental data
very thin region directly adjacent to the wall. And there we can use this direct relationship to obtain a skin friction value, which only has errors and uncertainties which are based from the velocity and the wall distance values. So the surfaces shown here have been shown to reduce drag below that of a smooth surface. The most successful is thin blades aligned in the direction of flow, which has been shown to obtain a drag reduction of about 10%. Three-dimensional surfaces have also been shown to reduce drag reduction, but to a lesser extent. The main disadvantage of all the surfaces shown here is that there's a very high cost in manufacturing, and there's also extremely low wear resistance, which makes them unsuitable for contact applications and also very prone to damage. One of my main interests is expanding into three-dimensional texture geometries for similar purposes. Unfortunately, there's an additional complication here where with three-dimensional geometries, an additional component of drag is considered called the form drag, and this adds to the viscous drag, often to increase the total drag for acting on a surface. As you can see here, for these three-dimensional cubes and three-dimensional hemispheres, the high velocity fluid in red and the low velocity fluid in blue, the low velocity fluid forms recirculating low pressure regions behind the geometries, which causes a pressure difference and hence a pressure force to act along with the viscous drag. Both of these surfaces, unfortunately, did increase drag far above that of a smooth surface. And so we've got to bear in mind that our main aim is to decrease the viscous drag, as has been done previously, but minimise the form drag that would be created by these three-dimensional geometries. So how do we measure velocity in a boundary layer? The first method I want to talk about is hot wire anemometry, where a wire is placed in the flow and is supported between two metal prongs. It's about 5 micrometers thick, and the temperature of this wire will change with the fluid velocity, and hence the voltage will change with the temperature and therefore the fluid velocity due to heat loss from convection. And through recalibration, we can then compare velocity values and obtain voltage values in the wire and obtain velocity measurements. And we can obtain very high frequency velocity measurements, and therefore we can then get a time averaged value of velocity. Alternatively, we have the pressure probe technique, which consists of a hollow tube with its opening aligned with the direction of the flow, and the difference between the pressure flowing into the tube and the pressure of a static fluid can be used to determine the velocity. There are sources of error due to the tube disturbing the movement of the flow due to its physical presence. However, there are extensive correction equations to account for this. The main another key advantage is these tubes are extremely cheap and quick to implement, which means they are ideal for industrial applications and preliminary analysis. Unfortunately, the size of these tubes does make them usually unable to access the viscous sublayer, and as shown by Bailey et al., even if they could, the error in the inner region is approximately 3%. So ideally, we want to obtain velocity measurements in the viscous sublayer and do so using hot wire anemometry. Unfortunately, the limitation is that, as you see, as the probe approaches the wall, the measured velocity significantly increases due to increased heat loss into the wall. This, unfortunately, limits the region of the viscous sublayer that we can obtain a decent measurement in. The one key advantage of these effects is points A and B here. The sudden change in velocity gradient indicates the point where the prongs make direct contact with the wall. And by observing this error profile, we can then, it's been shown we can predict Choi have shown that for a very slow speed, very thick boundary layer, a single measurement in the velocity in the viscous sublayer can be used to obtain the skin friction to an accuracy of approximately 1%, which is still, compare that to the earlier results of the chet for 10% drag reduction, it's still quite a significant, it's still quite a significant portion of the observed drag reduction. Okay, just very briefly, an additional, when we introduce texture geometries, we have to determine the techniques developed by Hutchins and Choi are not necessarily valid because the actual wall location in textures is not located at the solid surface. It is theoretically shifted down along the entire profile below the roughness crests. This makes the original wall location, so should we say, very difficult to locate, and further limits the useful region of the viscous sublayer, as well as increasing the total error in the skin friction measurement. So, in conclusion, in our best case scenario, where we have Merchet's 10% drag reduction and Hutchins and Choi's 1% skin friction error, we would still see significant magnitude of error compared to the drag reduction we're trying to observe. The existence of the origin of the shifted wall position, or what we call the origin offset, could significantly increase this error, making it potentially very unreliable and unsuitable for the analysis of drag reducing surfaces. So in conclusion, it's very difficult to obtain accurate measurements of skin friction for two-dimensional geometries, and therefore we should always obtain a direct measurement of skin friction, usually with use of an approximated false visa, which of course does have its own problems. Alternatively, though, for three-dimensional geometries, we've been able to obtain independent measurement of viscous drag, as we would have to obtain total drag and then separate the viscous and form drag components, making analysis far more difficult. Any questions?
So we've got time for about two quickish questions. Anybody got a question to ask? Yes, please, James.
Bill, so you displayed an array of physical intrusive methods, but are there any non-intrusive methods which you might think are applicable to what you're doing?
Yes, there are several. There's one in particular, laser Doppler anemometry, is considered to be one of the most suitable. In fact, we're actually supposed to be receiving a laser Doppler anemometer at this university in a few months' time. And the main advantage is obviously we can obtain more accurate measurements, and it doesn't disturb the flow. The disadvantage, though, and why I focused on invasive techniques, is laser Doppler anemometry can be horrendously expensive, of about £150,000 to £250,000. And so, but when you look at industrial applications, or it takes a long time, obviously, and it's difficult to set up. And so when you look at industrial applications, or just preliminary analysis over for a lot of different surfaces, then it becomes very inefficient in terms of cost. So that's why we may choose more invasive methods.
Any other questions, John?
Yeah, can you just clarify from the early slide when you showed how the flow develops sort of left to right and away from the surface? Yes, that can be.
Yeah.
How does that relate to what you're trying to do with the hot wire probes? Do you just like trying to get a profile of what speeds are?
You this is usually done in a wind tunnel, and you this is the theoretical the shape, the form of the No, there's difficulty, particularly with hot wire anemometry, is it's actually locating. As I mentioned with Hutchins and Choi, what they showed, actually locating the position of the wall relative to where you're measuring is extremely difficult, and that's why this method is extremely vital, because it allows us to detect. The probe will tell us exactly when it has touched the wall. So to bring it down to the wall, detect where the wall is, and then start bringing it up and measuring the velocity profile.
Okay, I have to call an end to it there. Thank you very much, Philip.
Our next